Whoops.
Helpful pertaining to what? Helpful pertaining to what?
For pertaining to expanding carbon structures. Why are alkynes useful for adding carbons to a structure?
Because you can make it a nucleophile.
Yeah. We can turn that terminal alkyne of a carbon, that bond is much more polar than any of the other functional groups, such to the point that we can actually make that acidic, and we can add a strong base like sodium amide. Okay, there aren't a whole lot of bases that you would typically see used in this case. Pretty much the only one that's really of relevance is sodium amide. So if we add sodium amide, that will pull off the hydrogen, putting all of the electron density on the carbon. We now have that nucleophile. So it's yet another way to generate our carbon nucleophiles. Again, fairly rare, and be aware of the level of the reagent. You're looking at using a really strong base to generate that. If we go through and look at the resulting product, that product is now also a really strong base. Okay? It's not just a nucleophile. If we look at the Grignard reagents, they have the same kind of issue. Okay? So you generate a negatively charged carbon. That means you got a nucleophile, Lewis base, and Bronsted base. So be aware of all of those individual chemistries because they can throw a wrinkle in what you're trying to work with. I tried to summarize all the main functional groups and actually post that up there because it sounded like we had some issues figuring out what functional groups are important and what ones aren't. So I tried to make sure I included all of the major ones up here so you'd be aware of them. You should have these memorized so that when we start talking about them in class, you know exactly what we're referring to and what different things happen. Okay? So spend some time, make sure you've got them memorized if you haven't already. There are undoubtedly more, but I picked kind of the big ones that we'll be discussing. So we've kind of finished looking at alcohols as far as the synthesis of alcohols go. The next part that kind of has a small little section is looking at reactions around alcohols. So for instance, if we started with that species on the left, right, and we wanted to turn that into our product on our right, what changed? What did we do? Okay, we've got some R groups in there. So somehow or another, we would have to react this species with some R groups. Okay. What charge would those R groups likely be? If we go to our product and evaluate the chemistry and what's going on there, we have an oxygen-carbon bond. That carbon is most likely partially positive, which means in the course of this reaction, those R groups would need to come in as negatives. Okay? So we have to somehow get this reaction to work or come together by piecing those things together. One way we could bring in our R groups would be to introduce a Grignard reagent. The problem with the Grignard reagent, any ideas? That alcohol is problematic when it comes to a Grignard reagent. Why? Particularly the hydrogen. What's the partial charge of that hydrogen?
Partially positive.
Partially positive. Which means if I try and bring in a Grignard reagent, okay, a carbon negative, that negative is going to react with the most positive thing present. Hydrogens are extremely accessible and very easy to pull off in this case when they're bound to an electronegative element. So if we've got that extra alcohol floating around in our structure, we're going to end up neutralizing our Grignard reagent. We don't get a reaction to occur. So what we want to do is somehow protect the alcohol, prevent its chemistry from actually occurring. So what we're going to effectively do is turn it into a less reactive functional group. What's a less reactive functional group that contains an alcohol or contains an oxygen? We haven't talked about yet, chapter 14.
An ester?
We could go as far as esters. What I was looking for in this case was an ether. Okay. Ethers are going to be a little bit more simple than an ester. The ester brings in the added chemistry of the carbonyl. So what we're going to do is effectively generate an ether. That ether functionality will neutralize the acidic hydrogen because it won't be there anymore, and we can then try and propagate our chemistry out. So what we want to do is protect first. So what we're going to do is change the chemistry of that alcohol, put something else on there to neutralize that alcohol effect. So that's that black box. Then what we'll do is run our Grignard reaction. That Grignard reaction gives us the nucleophile. We won't have to worry about the acidic hydrogen on the alcohol anymore because our protecting group is hiding it. And we can finalize the whole reaction by then deprotecting. So our protection scheme has two big goals. One, neutralize the reactivity, but then also be reversible. Because if it's not reversible, we may have protected it, but we can't get it back, so that defeats the purpose. Okay. So the most common, or the only one we're going to look at for protecting our alcohols is going to be looking at trimethylsilyl, or TMS. Works fairly well as a protecting group. It's not officially an ether, but it's pretty close as far as the chemistry goes. Why would I say it's close? Where's silicon on the periodic table? Right underneath carbon, so it's going to act very, very similarly. Okay? And we pick something like silicon as opposed to carbon. It's larger, which means we're going to have slightly larger options as far as chemistry goes as well. If we put on a carbon, that becomes a lot more difficult to pull off because it's that smaller size. So this reagent can be added or reacted with our alcohol and put on that protecting group. You'll see it abbreviated as TMS, just because that's its name. To get it in there, that silicon needs to be reactive. And what we're trying to do is to get it to swap for the hydrogen. So to do that, we need something that's relatively positive. Okay, silicon's a good source in that case. We want to attach it to something electronegative, hence our halide. So our reagent will be TMS chloride. That chloride can now act as a reasonable leaving group. And what we can go through and do is have the alcohol attack the silicon with that lone pair. That can kick off our chloride, our intermediate. It's going to look like a mess here. And then our 3 methyl groups hanging off. Is this species going to be stable? What's missing from it? Positive charge on that oxygen. It's got 3 bonds. We want to eliminate, again, that hydrogen. That hydrogen needs to be removed from the structure. How can we remove the hydrogen? That hydrogen would be acting as a Bronsted-Lowry acid. What should we react it with? Bronsted-Lowry base. So step 2 of our reaction is to add a weak base. In this case, triethylamine. You might also see that abbreviated as, any ideas? You might see it abbreviated as T for triethylamine. That can remove that last hydrogen because our nitrogen has that lone pair. When drawing our arrows, notice we're starting at a source of electrons and ending where we lack. And we now have our officially protected alcohol. We could then take this compound on and react with other species. Before we look at that, like our previous slide was looking at. Okay? One extra thing to consider here. So while protecting groups might be helpful, they can limit that chemistry. There's an additional issue. If we were trying to get across from start to finish, we try to do that in one step. We have one step where we can make a mistake, okay? And that's going to reduce some of our yield. What happens when we try and do a protection? We've got 3 steps. So we've got the one step where we actually wanted our chemistry to occur, and then we have 2 extra steps just to deal with the alcohol. So while protecting groups might be helpful in theory, one of the problems that you'll encounter, at least when you move into the lab, is that yes, that protecting group may protect it, but then I reduce the yield of the overall reaction because I have to run 2 extra reactions. Each of those reactions are going to potentially reduce the yield. You'll lose some in the solvent, you'll use some in a recrystallization. Okay? So when we're trying to design a synthesis, we want to minimize the extra steps if we possibly can. All right? Sometimes you can't get around it, so you've got to use some kind of protecting group. That's what we're trying to address here, is that there is a protecting group for alcohols. Does that kind of make sense? Okay. The next part is the reversibility. We need to get that protecting group off of it. Not a particularly easy task. So what we need is a particularly good or strong nucleophile. Our fluoride ion will work really well to go ahead and push that off. Let's see, actually draw the mechanism for that. Nope. If we take a look at our structure again, we've got our alcohol, silicon, and those methyl groups. Okay. We can go through either with H3O plus or F minus. F minus is one of the more common ones, so you'll see this reagent TBAF. Fluoride's not a particularly good or easy to supply nucleophile, and that's because it is relatively small, so it has a very high ion affinity. So it'll bind relatively quickly with whatever counter ion we have. So if we used a simple metal to set it up, that metal isn't going to be able to supply the fluoride ions because the metal is going to bind too tightly with the fluoride. The fluoride can't act as a nucleophile. So why do we go through and use tetrabutyl ammonium? It's really, really big. So it does provide that counter ion effect, that positive charge, but those butyl groups help kind of space the distance between the nitrogen and the fluoride away from each other enough that that bond is now weak enough the fluoride can act as a nucleophile, and it can now kick out our alcohol or kick out our oxygen, which can then later be protonated with another solvent like water. All right? The other option is using something like a strong acid, H3O+. How is that going to end up working? So our fluoride is a good old SN2 reaction. If we go through and use a strong acid, our first step is going to be to protonate that water or that oxygen. What's special about that protonated species? No worries. Does it want to be positive? No. So what ends up happening, we can bring in a good nucleophile, say like water, that can again do a backside attack and break the other bond. Okay, so our water can act to cleave our alcohol the other direction. Okay, or even actually go both directions in that case. Go out this way. So what you need to remember is just the combination of these two reagents. TMS chloride, which I believe we got on the last slide. Our TMS chloride followed by the ethylamine, or the triethylamine, to put on the protecting group. And then if you later need to remove that protecting group, that's where you'll use the TBAF or H3O+. Okay? Not going to be super common. It's just something that's kind of neat to evaluate. We do have ways that we can now protect these. We'll talk about protecting groups in more detail when we move into the carbonyl chapter. Now what we want to do is look at the reactions of alcohols. So we've seen how we can make alcohols. We've seen how we can protect them. Now what can we do once we have those alcohols? So the protecting group is mentioned before we look at these because put on a protecting group, we can't react the alcohol. So what are our possible chemistries? Okay, what could we break via acidity or acid-base chemistry? The easiest one to evaluate would be that OH bond. Okay, so we could have our alcohol act as an acid. Okay, what else could we do? We can break a bond via substitution. Where's that chemistry? We've got our CO bond. Make/break via elimination. What do we have going on there? We'll be making our double bond, and in the process we'll have to break our hydrogen bound to our carbon and that oxygen. So we have to do a whole lot of making and breaking to go through our elimination reactions. And the last one we can do is actually make a bond via oxidation. So we looked at how we could make an alcohol by reducing it. We'll now look at the opposite of that. What can we do with the alcohol as far as oxidation? Where does that take us? Okay? So looking at increasing the oxygens. You'll notice that a lot of that chemistry is centered around the functional group, which is one of the reasons when you go through and look at a functional group, you should be addressing these kind of ideas. What bonds can be made? What bonds can be broken? How does that change? What things can we do with it? All right? So we'll start with what I would say is the easier one, looking at our acid-base chemistry. We could break the oxygen-hydrogen bond via acidity. Okay? To do that, we need a strong enough base. If we use something like sodium hydroxide, the equilibrium isn't very favorable, which we've talked about, and that doesn't get us to our product, okay, or get us to that nucleophilic oxygen very well. So what we want to do is put in another base, or a stronger base. That stronger base is typically, anybody remember? Sodium hydride, so not sodium amide in this case. So we can use sodium hydride or just straight up sodium metal. Okay, they both will react very similarly, do the same kind of thing. They supply electrons through the sodium that reacts with our hydrogen. In the process of this reaction, we can generate our negatively charged oxygen, and we also release hydrogen gas. And we'll still have that sodium ion floating around. Okay. So, relatively simple chemistry, nothing particularly interesting in that on its own, except that we generate that negatively charged oxygen. What's special about a negatively charged oxygen? It's a nucleophile. So what we can do is now have that negatively charged oxygen react with an electrophile. And in the process, what we can do is potentially make an ether. This is known as the Williamson ether synthesis. So it allows us to make unsymmetric ethers. We'll talk about that again in more detail when we move to chapter 14. But effectively what's going to happen is if we start with an alcohol and we react this with, let's do this differently. An alcohol and we react this with our sodium hydride. In our first step, the result is we generate our strong nucleophile. That nucleophile we can now react with an electrophile. Could do something along the lines of, let's just do methanol. This can react, we kick out OH minus. And what we now have is our ether. Anybody have any problems with OH minus as a leaving group? Really? Nobody? Typically a bad leaving group. Why is that a bad leaving group? It's a strong base. Okay. What's another issue with this reaction as shown? Our nucleophile is reacting with what? The carbon connected to our oxygen, right? Which is our partial positive, so that's not necessarily a bad thing.
In the product,
why would the oxygen react with the carbon? What charge is the carbon?
It could be positive,
It's
partially positive because
partially.
it's connected to
To the oxygen?
oxygen.
Is there another partially positive atom in that structure?
The hydrogen attached to the oxygen on the other end.
In one case, we've got it acting as a nucleophile, or sorry, our methanol acts as an electrophile. On the other side, it acts as an acid. Which chemistry is faster?
Acid.
Our acid-base chemistry is faster. So while this seems like a reasonable idea at first, we've got a couple issues. Our hydroxide's a bad leaving group. Okay. Compounded further by our presence of our acidic hydrogen also limiting this chemistry. So how could we end up with that final product? We need to fix the bad leaving group issue. We still need an electrophilic carbon. How can I get an electrophilic carbon without bringing in an acidic hydrogen? Grignard generates a nucleophilic carbon. To make the Grignard, we needed an alkyl halide. What's the special part of our halogens? They're electronegative. They can draw electron density away from the carbon, which means the carbon becomes
Positive.
our positive, which is our electrophile, which is a good process. What happens for our leaving group? Now we've got a good leaving group. Okay? So process it as quickly as you can, but then evaluate. Go back and check each of your steps of your reaction. So when we're doing a Williamson ether system, that fancy long word, the WES, we'll go through and remove our hydrogen first from our alcohol to make our strong nucleophile. We'll then react that with an alkyl halide to generate our ether. Okay? That halide then won't react in our further reactions. Okay? Questions about them? So, simple acid-base chemistry that then turns into extra chemistry after the fact. Pretty sure we're moving to the next one. Said I was going to stop there. Let's push a little bit longer. Let's make the video about 30 minutes. Okay, substitution. We can break via substitution. To do a substitution reaction, we're going to need a nucleophile and a good leaving group. What was the issue we just addressed on the last page? Our OH is a very bad leaving group. Okay, so we could supply a nucleophile all day long, but that's not going to work very well for this reaction because we still have that bad leaving group. So what do we have to do first? We have to activate that alcohol to act as a better leaving group. What's an easy way to make it a better leaving group?
Turn it into water.
Let's make it water. What did the alcohol act as in this first step? Bronsted-Lowry base. Once it's now been activated, I have a good leaving group, and I can potentially react this with a good nucleophile. That nucleophile, depending on the chemistry, can either do backside attack and an SN2 type reaction, or if we had a poorer nucleophile, we might see an SN1 reaction, as long as we could generate that stable carbocation. Okay? So that's the easiest version for our substitution reactions. So very least, we must activate our alcohol before it can act as a leaving group. So to do that, we can either add our strong acids, so HBr and HCl are good options in those cases. Turns out HCl isn't quite, or the chloride isn't quite a good enough nucleophile, and so we need to activate that a little bit further. So when we go through and add our strong acid like HCl, we also have to add a zinc chloride as a catalyst. The zinc will help coordinate that oxygen and help pull it off so that the chloride ions can do that backside attack and pull it off. Okay? So our first two options are using bromide as our nucleophile and chloride as our nucleophile. Okay, so those ones you should be able to kind of guess. I know the zinc chloride's a bit of a wrinkle in that one, but that chemistry should be very familiar. The two new ones would be PBr3 and SOCl2. What do you think our nucleophiles are in those cases? As a hint, there's a reason they're organized the way they are. Yep, bromide and chloride also end up acting as our nucleophiles. Okay, so what's the rest of that junk associated with it? Okay, the rest of that junk is what's activating our leaving group, activating our oxygen for the substitution, for it to be able to be removed from the structure. Okay? Why would we prefer to use the strong or HBr versus PBr3 or vice versa? What if you have an acidic, or sorry, a basic element within your structure? Something that will react with a strong acid. Okay? If that's in your compound, does it make sense to add a strong acid? No, because it's going to push an acid-base reaction, which we don't want. We want to do just the substitution. So we'd have to come up with some other way to activate the alcohol without turning it into, or sorry, without bringing in the acid. To do that, PBr3 does a really good job. So we don't have to have the presence of that strong acid to allow for the reaction to occur. What happens in the case of SOCl2, also known as thionyl chloride? Same general idea. Thionyl chloride doesn't have that HCl, doesn't have the presence of that strong acid, at least initially, which means we can run through and do a chloride substitution without the presence of the strong HCl acid. Right, so it's just something to consider when you go through and evaluate these things. The last reagent on that case is a little bit more generic. Our nucleophile is coming in as a generic nucleophile. To get that last reaction to occur, to have our alcohol react with any generic nucleophile, it still needs to be activated. To do that, we can use this reagent, known as tosyl chloride. The chloride can be kicked off in a substitution reaction, so our alcohol reacts with the tosyl, kicks off our chloride. We now have a phenomenal leaving group, which we'll look at in a second. The nucleophile can come in and kick out the oxygen and the tosyl, and the tosylate. Okay? So it's just realizing what extra pieces we've got. If we take a look at HBr and even our zinc chloride, okay, each of those generate a positively charged species. Let's go with our red. So our oxygen has some extra lone pairs. In the case of HBr, we're looking at H+. In the case of zinc chloride, we're really looking at that zinc ion. Why is the zinc positively charged, or even partially positive? What's it attached to currently? Two chlorines. What can you tell me about those bonds? They're ionic bonds. Which one's positive, which one's negative? Chlorides end up taking electron density away. There's our negative, our zinc will be positive. Why does this help us? Well, our oxygen can either share with our hydrogen or our zinc, and we can generate a good leaving group in both cases. That good leaving group H or zinc can then be pushed out by using our nucleophile, which will either be our bromide or our chloride ions. You'll notice all of these reactions are occurring in an SN2 type formation. Okay, we're getting this backside attack. Why would we push the SN2 and not, say, look at SN1 reactions? This goes back to your understanding of substitution reactions from last semester. What's the issue with the carbocation intermediate in an SN1? How many products do you get? You get a racemic mixture. So if we had stereochemistry involved in this and we did an SN1 reaction, we get two products. Okay? Particularly if you're in any kind of pharmaceutical field, you want one product. We don't want two. So what we'll do is always design and build our chemistry around generating one chiral product. Okay, so a lot of the reactions we're going to look at are driving in this SN2 reaction instead of our SN1. Okay? And we've got our substitution in both these cases. Questions about those two? If we go through and compare HBr versus PBr3, okay, what's happening in the case of PBr3? Well, what can you tell me about that phosphorus in the middle?
It's not a partial positive charge.
Why is it partially positive? I see a lone pair. If it helps, you're right.
You still got the electronegative bromides pulling the electron density.
You've got 3 very electronegative bromides on the outside of that pulling the electron density away. Okay? That makes that phosphorus partially positive. It's also relatively large, which means that we have a little bit more space in there as well, that we can slide the electrons from our oxygen into it. Phosphorus would then have too many bonds, so what happens? We break off one of our bromides, and we end up with a pretty good nucleophile in the case of our bromide, and we also have a pretty good leaving group in the case of our phosphorus compound. One of the things that's nice about our phosphorus tribromide, how many bromides are on the phosphorus? 3, which means for 1 molecule of phosphorus tribromide, we can bring in 3 bromides. So we get a slightly larger reactivity or a larger, lower ratios, less chemicals need to get used in the case of the phosphorus tribromide, because each of those bromides can be used to substitute. Okay? Why is this better than the HBr? We don't have a strong acid at play. We do generate that acidic hydrogen up there at the end, but it's an alcohol acidic hydrogen. Okay, so our relative acidity within that solution is still closer to neutral than the strong acids. Okay, so it's kind of a nice effect. Again, you'll notice that it is in an SN2 type fashion or type reaction. We get that backside attack and the kick out of our leaving group. Okay? So our first step with all of these substitutions is activate the alcohol, then push the substitution reaction. Questions about that one? What happens in the case of our thionyl chloride? Again, draw out the structure. See what you're working with. Sulfur's in the middle. We get our oxygen and our 2 chlorides. What's special about this molecule? See any potential sites of reactivity? First step for all of our reactions has been activation of the alcohol group by having the alcohol react with what kind of a species? What charge is that species that it's reacting with?
Partially positive.
Positive. Is there a partially positive or formally positive atom in here? Not a formal positive. Do we have a partial positive?
Sulfur.
The sulfur. Why would the sulfur be positive?
You get the electronegative chlorines and the oxygen there.
You've got the electronegative chlorines drawing electron density away. Take it even further. We don't even have to look at how electronegative the oxygen is. We could look at resonance. We can actually draw a resonance structure where we make that formally positive. Why does this help with us? We can go through, whoops, actually I do want that color. The lone pairs on our oxygen can again attack. The first step is going to be to break that sulfur-oxygen bond. Why would we break that bond first? What was that? It's a pi bond. Why should pi bonds be broken first? What?
Is there easier to break?
Why are they easier to break? I didn't hear that. Because they're nucleophiles?
It's weaker because of the way the bonds overlap.
The bond overlap is weaker, which means they're an easier bond to break. So we end up breaking that bond first. Our sulfur is now even more positive than it was to start with because we've added another oxygen. So what can happen? Can shuttle this electron density down, and we can kick out a leaving group in the form of our chloride. And in case you were wondering, yes, that oxygen is positively charged. Okay. This generates an interesting product, okay, or an interesting situation here, which is why I want to address it. Thionyl chloride has some kind of bizarre chemistry. If we've got the situation that we've got here with nothing else present, this chloride does break off, partially negative, right? Is there something partially positive very, very close to it? Which is why I picked this chloride. Go ahead.
The hydrogen and carbon.
We've got the hydrogen and the carbon. Okay? The carbon is going to be our important feature in this case. Why would we look at the carbon? If we take these electrons and immediately kick there, how many bonds does that carbon have? 5. Is that a good thing or a bad thing? Well, it's pretty awful, so we want to break a bond. The bond that we want to break is going to be the most polar or easily broken bond. What bond would that be? The one to the oxygen. Okay. This brings up an interesting dilemma. Okay. What happened as far as the stereochemistry goes? Let's say that that carbon-oxygen bond was wedged. What would our product carbon chloride bond look like? Okay. To either show it as wedged or dashed. Which one's correct?
So the carbon oxygen was wedged.
The carbon oxygen was wedged to begin with.
Wedged.
Ends up being wedged. We get retention of stereochemistry. Very, very odd. Very few reactions generate a retention. That chloride would slide in directly over the top of our oxygen, and we'd end up still with a wedged bond. Okay? And I'm going to add some extra words in here that we'll discuss in a second. There are other conditions that end up generating the dash, which would be our inversion. Okay? And as a hint, you've got the condition right there. How do we get inversion of stereochemistry? Let's make sure we have the presence of a base. The base that is typically added in the case of these reactions, oops, let me draw that a little bit bigger, is pyridine. It wasn't that much bigger. It's a fairly weak base. The lone pair on that nitrogen can pull off the acidic hydrogen before we kick out the chloride. Why would that be important? So in the presence of a base, we do our deprotonation and we end up with our carbon-carbon. Again with our wedged oxygen, sulfur, chloride, and we still have our chloride now floating around. As we break that chloride bond, would we have a particularly good leaving group, or as good of a leaving group out there? It's not quite as nice because we don't have that positive charge on the oxygen. What does that mean? The chloride bond breaks off and has just enough time to actually attack from the back side of the bond. And we end up seeing inversion in the product. Okay? So this is a tricky one to watch out for. Okay? And I'm going to have to take a look to see exactly how the ACS test addresses it. So let's erase everything for a moment. If we go through, let's specify some stereochemistry, we put in a wedge there. If the chemicals we used are just listed as SOCl2, first off, what's the net result of this? We get the substitution. The chloride is substituted for our oxygen. What's the stereochemistry? There is no base, so retention of stereochemistry. How would you know that you were expected to draw the other one? You would see SOCl2 followed by PY for pyridine. You might also see it drawn out. That's going to end up giving you the inversion product. Okay? So those secondary features in a reaction can have a huge impact in your overall results. So be aware of that, particularly when you're looking at SOCl2. Okay? You can see both retention and inversion depending on your circumstances. Okay? Questions about that? Last one I want to address real quickly here, our tosylate. What we're looking at, chloride. Yes. Am I drawing that right? No, I've already, here. Because I'm not positive I got it right. We'll just abbreviate, be obnoxious about it, and I'll draw it in later. Our tosylate acts as a large group. Oh, just remembered it, sorry. We're again introducing that sulfur. Our oxygen can come in and attack that sulfur compound. It can then kick out our chloride leaving group. And what we'll end up with, because typically most people are lazy when drawing this out, we'll have OTS. That OTS is now a really good leaving group, so we can also now add some kind of nucleophile in the course of this reaction. That nucleophile with its electrons can come in again, SN2, and we do our substitution reaction. Okay? The tosylate is there only to make our alcohol a better leaving group. Again, why would we use this reagent? No acids, no bases. Okay, so we're keeping the pH of our reaction relatively neutral, which is nice because our acid-base chemistry can mess with everything. Okay? You'll notice that you might also see pyridine thrown in there. Why would the pyridine be there? Again, with that PY. What's the one thing I didn't show? Officially, I didn't show that. There's another thing I didn't show. What was the pyridine used for previously? It's a base to remove your acidic hydrogen. When does it remove it? Does it remove it before the reaction or after it's formed? It's kind of a harder question.
Isn't it after?
It's going to be after. Why? How acidic is that hydrogen? We compare the acidity of this hydrogen and our starting material. So we'll call that hydrogen number 1 versus hydrogen number 2 after the first step. Which one's more acidic? For it to be acidic, the conjugate base needs to be more stable. If we look at the conjugate base in step 1, what is it? O negative. Okay, charged. Is that a particularly stable thing? No. What's the conjugate base in our second step? OTS. No charge. Which one's more acidic, first or second? Second. It's generating a more stable conjugated base. Okay? Why would we not predict to remove the acid right, or that hydrogen right away? Do we see a base? There's no base in solution. Remember, we're running at virtually neutral pHs. To remove that hydrogen, we'd need to add a strong base. Okay? So it's going to get removed in our second step once we've increased the acidity of it enough that a weaker base can pull it off. Okay? Kind of makes sense? So for each of these reactions, what we're trying to do, what's our commonality? All of these involve that pre-reaction. Our oxygen is going to act as a nucleophile or a Bronsted-Lowry base, react with something positive, turn that oxygen into a reasonable leaving group, then we can have our nucleophile attack. So it's not as straightforward as our alkyl halide chemistry was. Okay? And because of timing on this, I'm just going to decide to do the quiz at the very end. I changed my mind. Okay? Questions about our substitutions with our alcohols? Net result for each of these. What are we substituting when we used our strong acid HBr? Our alcohol for bromide. When we use zinc chloride and HCl, what are we substituting for or with? Our chloride is coming in. PBr3, bromine, SOCl2. Our tosylate. That one's kind of tricky. It's whatever our nucleophile is. Okay? So when you see these reagents, you should be first off triggering that it's a substitution reaction, and then be aware of what piece is actually coming in and doing that substitution. Okay? What's a red flag that it's a nucleophile? What do all nucleophiles have? What was that? Negative charge. Okay? If it is something that is relatively negative, or partially negative, lone pairs, we're probably looking at our nucleophile. Okay, so that's our substitution reactions. Our eliminations, effectively the same as our substitutions to a certain extent. We need that good leaving group, so we're going to have to pre-activate just like we did with our substitutions. Okay, so that bond has to break. What other bond has to break in an elimination? Our carbon-hydrogen, which can then allow us to form our pi bond. Okay? So how can we make our alcohol a good leaving group? What could we do? Okay, we could add H+. Great. That can protonate it. We now have that good leaving group, and we can potentially do the elimination. If we add H+, how do we break the carbon-hydrogen bond? What is our carbon-hydrogen bond acting as? Is it a base? Electrophile, nucleophile. What is it? It's acting as an acid. How can we get it to act as an acid? React it with a base, right? Makes sense? Anybody see an issue with that? Don't write that down. What do we do to activate our alcohol? You added an acid. How do you break the carbon-hydrogen bond? Add a base. What happens when you mix the acid with the base? They neutralize. You just added water to your alcohol. You're going to get your elimination. No. Okay? So when we go through to do eliminations with alcohols, we cannot bring in a base. Bases are going to, or at least initially, we can't bring in the base because it's going to react with whatever was making our alcohol a good leaving group. So what's the partner with our acid to help break that carbon-hydrogen bond? They both begin with H. That was a good call. But there you're wrong. Or that delta symbol. We can add a strong acid to to help activate that leaving group, but then to break that carbon-hydrogen bond typically requires time or heat or other features to help kind of push the alkene formation. Okay. What else could we potentially do? Were there other activating reagents? We could do a substitution, convert the alcohol into bromide or chloride. Then we could go through and add our base with our heat. That would allow us to do that elimination. Why is the base then not a problem? We don't have the alcohol. Okay, so we could convert to an alkyl halide first, then do the base elimination. Okay, what's another option? How else can we treat it? Convert it to our tosylate. And then we can bring in base. Okay? As long as we have the alcohol present, we can't use the base. So what we can do is get rid of the alcohol. Do our substitution first, get our alkyl halides, where we don't have that acid-base question to worry about. Now we can bring in our base, do our elimination. Okay? So our tosylates will work as well as converting it over to the halides. So what we end up doing is getting rid of our alcohol before we can initiate our reaction. Last one to look at was looking at the reactions of alcohols. We can make them, we can make a new bond via oxidation. So when we looked at our reduction side of it, we went through a whole bunch of different stories on that. I did such a great job explaining those oxidation states. In theory, that makes a little bit more sense to you now after you've watched the video. But again, completely unnecessary, because you could evaluate your starting material and your product and say what things changed. And that covers probably 90% of the questions you see. So if we take a look at that very first reaction, should have boxed this slowly. What's happening? What changes in that very first step? We've lost a carbon-hydrogen bond, so we've lost H minus. I'm not going to draw it as H minus. We lost H, and we've also made a carbon-oxygen bond. We've increased the oxygen, decreased the hydrogen, oxidation. Don't need to know anything about oxidation states. What happens in the next step? So here's where we got to be careful. I heard we gained an oxygen, and I've heard we gained an H and lost an H. Okay, where are we looking at when we're looking at this reaction? About what atom? About the carbon. So around that carbon, what happened? It lost a hydrogen and it gained an oxygen. What's that last hydrogen out there? Where did that come from? That's there only to stabilize the oxygen. Okay? By putting on that second oxygen, remember, oxygen needs two bonds. That hydrogen at the end is just there to stabilize that oxygen, and what we're left with is that carboxylic acid. So when we go through and oxidize alcohols, we've got the potential to do two oxidative steps. Okay? What happens when we move to the next case? What's the net reaction here? Well, we've lost a hydrogen, and we gained that carbon-oxygen bond. If we try and do the next step, remember our rules. We have to lose a hydrogen. Is there a hydrogen attached to that central carbon now? No. So what happens? Nothing. There is nothing to easily oxidize. So what happens? Our reaction stops. There is no extra oxidation. It stops at the carbonyl. What happens in the very last case where we have a tertiary alcohol? Now there's absolutely no hydrogens on our carbon, which means we can't increase the number of oxygen bonds. No reaction occurs. So when we're looking at the reactivity of our alcohols, it's important to classify them as our primary, secondary, and tertiary. Our primary alcohols have the potential to oxidize twice. Our secondary can only effectively go once, and our tertiary just don't have the ability at all. This is why that rule on reduction being increasing hydrogens and decreasing oxygens, and oxidation being decreasing hydrogen and increasing oxygen is very helpful, because we can pull back to those rules and not have to worry about the adding, subtracting, multiplying, dividing, whatever you got to do with those lone pairs that the textbook like to go into with the oxidation states. Okay? So now that we know the potentials for these, we want to come up with different reagents to react them. As far as you're concerned, there are two oxidizing agents for alcohols. You've got chromic acid, and then you've got pyridinium chlorochromate. Okay? I like to refer to the last one, PCC, as politically correct chromic acid. Because if we had politically correct humor, it's typically not quite as funny, right? A little bit milder, not quite as abrasive. Same thing's happening in this case. Chromic acid will oxidize the crap out of anything it touches. If there is a hydrogen, it will remove that hydrogen and replace it with an oxygen. Okay? As long as we have that polarity already established, okay, with our alcohol. PCC, on the other hand, will only oxidize the carbonyl. It cannot go further than that. Okay, so it will stop after that single oxidation step. Whereas our chromic acid, if we have a primary alcohol, it's going to push all the way to the carboxylic acid. It cannot stop at just the carbonyl, okay, or in that case, just our aldehyde. What happens if we put it on a secondary alcohol? Well, it's still going to go through the same idea, pull off as many hydrogens as it can, and put on oxygens instead. There's only one hydrogen to remove, so we only get that one oxygen bond. Okay, and we get that one oxygen bond in the form of a carbonyl. Okay? So as far as these two reagents go, I think it's easiest just to memorize what's going on with them. There are a variety of ways that you'll see these. Pyridinium chlorochromate, 90% of the time, is just shown as PCC. Okay? I very rarely have ever seen that written out in its entirety. The chromic acid shows up in all variety of different ways. I've seen it as H2CrO4, the dichromate mixed with acid and heat. I've also seen it as H2CrO3. They're all doing effectively the same thing. We're oxidizing that alcohol across into a carboxylic acid. Okay? Why does PCC not push all the way? Okay, well, what's the difference between those two reagents? Okay, one thing that might be helpful is we drew out the pyridinium. So we said pyridine was that species. Pyridinium just means put the hydrogen on it. What's the difference between pyridinium chlorochromate and chromic acid? What's the acid in chromic acid? Don't tell me chromic acid. That's cheating. The H what? To generate the reactive species of chromic acid, we need sulfuric acid. What can you tell me about sulfuric acid? It is a strong acid. When we move to pyridinium chlorochromate, what acid do we have? We have the pyridinium ion. Is that a strong acid? How do you know it's not a strong acid? It's not one of the ones you're told to memorize. It's the easiest way to remember your strong acids. Okay? It's not one of those 6 or 7 you had to memorize. So what happens? Because we see that acidity difference, that changes the chemistry in the subsequent steps, and we end up not allowing for the second oxidation. Okay? Like 90% certain this is the end of it. So I'm going to real quickly draw this up. We'll start with just a standard alcohol. The alcohol has lone pairs. Again, this is one you're not super responsible for, but it's nice to see. And we can do subsequent protonation, deprotonations. And we eventually end up with something along these lines. Okay, our chromate intermediate. Okay, the fun part on this is that we can remove with a weak base. Turns out it doesn't have to be all that strong. We can break that carbon-hydrogen bond, take those electrons, and put them into that pi bond. Why would that happen? How many bonds would that oxygen then have? How many, or what would its octet be at? It would have 10 electrons around it. Can it have 10? No. What happens? Chromium takes the electrons away from that oxygen. The result is that we end up with our carbonyl and we generate this chromate ion floating off on the side. Why would chromium take the electrons away from that oxygen? What charge is that chromium? What's it attached to? A lot of oxygens. So much that in fact it's becoming extremely electron deficient, and it will actually enhance that electron removal from the oxygen. Oxygen doesn't want to become positive, so it will steal electrons from its most available source. The easiest way it can get them is by pulling from a hydrogen. Okay? So what happens if there's no hydrogen? Well, chromium doesn't have an electron source to take, and it ends up dissociating. That complex falls back apart, and we go back to what we started with. Okay? So as long as we have that hydrogen available, we can stabilize the removal of the electrons away from that oxygen into the chromium, and we change our oxidation states. Okay? The strong acids are what help facilitate the removal of our leaving groups in the process of this reaction. If we have a weaker acid, it doesn't allow for as good of a removal for our leaving groups, and we end up stalling out. Okay? And I am going to leave it there. So we did finish 14. So I've got our alcohols all kind of summarized. You'll notice there's a bunch of other stuff on there, for instance, that we haven't talked about. I wanted to say I talked about the osmium tetroxide, but I'm pretty sure I didn't talk about that. That's a standard diol reagent. It'll react with your alkenes. I've noticed that the second part of that reaction, the number 2, I've listed one reagent here. There's like 3 or 4. Okay, so if you see osmium tetroxide, you're going to the diol. Don't worry about anything else. That's what's happening. The other option, you can use the permanganate. I'll leave you to kind of evaluate that section on the diols to see what's going on with that. The MCPBA up at the very top, that's in chapter 14. We will talk about that through Wednesday. Okay? So what I tried to align with this is we've got our synthesis of alcohols kind of up at the top on how we can make those, and underneath we've got all the reactions thereof. So we looked at having it react as an acid to generate our strong nucleophile to make our alcohol, our ether. So that step was our Williamson ether synthesis, which we'll see again in 14. We've got the addition of a strong acid. That strong acid can give us, if we don't have a nucleophile, our elimination product. Or if we have a presence of a nucleophile, we can do our substitution. We've got thionyl chloride in there. Doing our substitution again, PCC will do our oxidation. And you'll notice that we're definitely missing some reagents there, the PBr3 and the tosylate. I will go through as soon as I can and get those added into this, so you've got those as part of the flow chart of what things can happen. You are ultimately responsible for knowing what every single one of those reagents do when they react with alcohols. and the subsequent reagents thereafter. Okay? Every one of our functional groups is going to have some messy diagram along these lines. Okay? You need to remember each of those reagents and apply them as necessary in each reaction. The very last on this one is your oxidation supplement. Okay? Just because it didn't quite fit in there. So this tries to go through and establish all the individual reactions that can happen from your alcohols. Okay? So those R groups are specified in the answer as well, or in the reaction. So if you use chromic acid with that, if your R groups are carbon and 2 hydrogens, what type of alcohol did you start with? A primary alcohol. What happens when a primary alcohol reacts with chromic acid? You get your carboxylic acid. What happens if it's 2 carbons and a hydrogen?
Secondary.
You have a secondary alcohol, your result. Tertiary, what's the result? This is something to watch out for. Okay? It looks like there's a result. I drew something, right? Okay? It's often labeled as no reaction. That doesn't mean you don't draw anything. Okay? So you might see something drawn as an answer that is the same thing as your starting material. What they're trying to say is that there was no reaction.